me if you want. This is going to be pretty straightforward, but it'll give you a pretty good idea of the importance of the dataset splitting. Okay, so what do I do with load iris now? So if you remember, I just call it, and iris is an object with a bunch of variables in it. Actually, it's a dictionary that has the data, the target. Data is basically the input, the X, target is Y, and feature names and target names. So data, shape, iris, target, shape. So we have 150 inputs that look like this, right? So we have 4 measurements that we're tracking, and we have classes. There you go. So far, so good. So what I'm gonna do now is I'm gonna say features train test split. So X train, Y train, X test, Y train, Y test equals. So what do we have here? So the inputs are, what should I do first? I have iris.data, the second one, target. And then we need a couple more things, which is sample test size. So I'm going to ask for 33%. And the other one will be shuffle. I'm not going to shuffle just yet. Okay, unexpected error because, okay, split. So let's check. Good, right? So we get the test split, 33. So let's see that we actually get what we wanted. It was good, right? So 100 samples in the feature set, train set, it's just inputs, 50 in the test set, 100 labels in the train set, 50 labels in the test set. Okay, decision tree equals decision tree classifier, DT fit. What should I pass here? Xtrain. Okay. All right. So now we have metrics. So that's a classification. We don't have classification metrics yet, so we're just gonna have to use one of the existing ones from the scikit-learn. So metrics, import, accuracy score. You remember what the accuracy is? How do we calculate the accuracy? Now, we not only can calculate R squared here because it's not a regression. What is our metric that how do we judge ourselves?
The accuracy would be...
So confusion matrix is a different way of looking at it. It's like a matrix, but there's one number. Remember, we're looking at one number.
You took like probability over the number of samples, but with the number of samples, right? Number of the test runs.
So there is this number of samples, yeah. So what is the accuracy?
Number of runs over the total number of tests.
Yes. So it's a real simple metric. How many we get right divided by the total number of attempts. So if we got everything right, it's 100. 1.0, if 0 right, it's 0, or anything in between, right? So that's all it does. Let me just do it here. So write this formula. So first I'm going to calculate the accuracy in the train set, right? How would we do it? First, we'll now predict our train set, right? So this would be ypred. And we have some predictions, so whatever. Then I'm going to calculate ypred equals to y train, right? So this compares value by value, what my predictions are to what I actually expect, which is y train. And as you can see, we're good, we're great. Well, it's not great because you now know the decision trees do that often, but we got every single right. If we sum this up, the NumPy treats trues as ones and falses as zeros. So this does the very natural thing, gives us number of correct predictions. And if we now divide it by the size of this, which could be y train shape 0, we'll get 1.0, right? And just to use this accuracy score function, just to confirm that we did the right thing, so true is first and the prediction, we should get same one. So please remember this formula, you'll practice it at home, and it will be on the test. It will absolutely be there, including with the confusion matrix. Okay, so what are your guesses about our test? So let me do the accuracy score, y test, and what should I compare it to with first? If I want to see my test classification error or accuracy. What's the, right, so there would be dt predict x test as the inputs. All right, what are the guesses what this would be? Because obviously it's not going to be 1. Why? Hold on. So what are the, like, yeah, so we trained the tree on the train set, 66, 70% there, 30% in the test set. Our prediction on the train set is 1.0. We're probably overfitting, but okay. This is actually a simple data set, I'm going to remind you, so it's not going to be, it shouldn't be too bad, even if it overfits a bit. Any guesses between 0 and 1? Make a guess. 0.6, 0.3, 0.9. All right, 0.3, 0.6, 0.9, I think. Any other guesses? All right. And the right answer is 0. Wow.
Good job.
Good. What just happened? We get 0 correct responses in our pretty simple data set of 150 samples in decision tree. Imagine that. All right. Any guesses? Okay, maybe not shuffle it. Okay, why would not shuffling be a problem?
We didn't account for even 2 1s because the first half.
Okay, there you go, right? So let's take a look at Y train. This is our training set. Let's look at Y test. This is our test set. Well, our tree never ever seen 2s, so it doesn't know they even exist. So it only can predict what it sees, right? So it only knows about 2 classes. So there you go. Here naively I took my data set, split it kind of nicely, ran my model, and I get the terrible result. And now, you know, I might be very confused about what's going on. So in fact, if we will take our model and say predict, and we will pass X test, we'll get all 1s, because that's the best it can do. It never knows that the class 2 even exists. And of course, we'll get 0 accuracy. So, and that is because, as you could see here, well, not here, but on the original labels, which I've shown you for a second, but then I hit it. Iris, target. Right, they're sorted. So first are 0s, then all 1s, and then all 2s. So if I happen to split right at the 66.66%, I'll take all this off, and it will go to the test set. So it means my data sets are actually corrupted. So there are 2 ways to solve this problem. So that's, you need to be aware when you're doing the data set splitting. That's why we do shuffling, which is very, very important, because shuffling will solve this problem. And in fact, it will solve this problem almost all the time. So if I'll go back and I'll say shuffle true, so we shuffle the entire data set. And then after we shuffled it, then we split it. And in this case, ilog, what is this? Oh yeah, so in our implementation, we expect this iris data to be a data frame. So very easy to fix. Data frame, data equals iris data, columns equals iris feature names. So I'll call it df. df. Yeah, so basically this is what it is now. Instead of just matrix, it's actual data frame. And now I can pass it instead of a data here. Okay. So now my shapes have not changed. I still have 150, right? But if I will look at the labels now, much better, right? So now they'll randomly shuffled. I got 1s, 0s, and 2s right there in both data sets. So if I will retrain my tree now, it should be fine. So accuracy score still, ooh, hold on. So I fit it, and then dt predict x train. This is still 1. We're still overfitting, but that's slightly. But now we get 92 on the test set. So now we see all classes. So that's why shuffling is very important before we split data sets to avoid the problem like this. Let's go back. So here I did a different trick of selecting, which also you will experience. There's a second way, slightly more complicated to split a data set, and that is called stratified sampling or stratified splitting. There's a function in scikit-learn. We're not going to implement it ourselves, but please take a look at it, where we can say, I want to use my class variable as an indicator, and I want you to split my data set 70-30, 60-40, 80-20, the usual thing, using this variable as a stratification. What it'll do, it'll look at the rows of the same value, for example, all zeros, and it will split them 70-30. So you're guaranteed to have 70% of zeros in your train set and 30% of zeros in your test set. And it will go to rows that have this label 1, and it will split them 70-30. So now you're guaranteed to have 70% of 1s in your train set and 70% of 1s, 30% of 1s in your test set, and so on until it finds every single unique value. So this is called stratified sampling stratification. Randomization works very similar by random chance. It's less precise because you can have fluctuations, which is okay to use. Stratification makes it much more robust though, because if you have a class that has only a few samples, your randomization might simply end up pushing them all into the train set, and you might miss them completely into the test set. So if you have unbalanced classes, which is the key word, here we have balanced classes, 50 each, it's safe. If you have unbalanced classes, you almost always want to use the stratified splitting. So class number 0, class number 1, class number 2 here at the bottom. Yeah, so because I'm not doing that stratification here. If I were to do it, I would need to sort by class. Once I sort by class, they all become properly separated, and I just pick 70-30, 70-30, 70-30, 70-30. So here I'm just explaining the idea. So actually that's how I split it. So I didn't want to do the randomization. That's actually difficult for humans, easy for computers. For me, it was much easier to go here and pick 3 zeros, 3 1s, and 3 2s. So I did stratified sampling by hand. That's basically what it is. It's a fancy word for this technique. So gray ones, or barely blue ones on this screen, would be the test set, so that you need to make predictions for. And white ones is the train set.
You mentioned that shuffling will pretty much fix all of our problems in terms of like the data being corrupted or unable.
Not corrupted, but in this case, yeah, it's not going to solve all your problems. What I'm saying is if you do shuffling, you're going to end up better off than not shuffling.
Yes.
So in many cases, it's just going to, if your data set is balanced, it's going to be actually adequate. If it's not balanced, you need to look into more details how it's constructed. So shuffling is the good safety mechanism, right? But if you're looking at classification, I would almost immediately look. I will start looking at the frequency of classes. See if you have very imbalanced data set. If you have an imbalanced data set, the shuffling won't help you. You need to do stratification. But if they're balanced and they're large, let's say you have like 10,000, 10,000, 10,000, you're pretty confident that you're going to end up with a good subset when you just do shuffling.
What was the terminology that you used? Stratified?
Stratified, yes. Stratified sampling or stratified splitting. Stratified shuffling. So scikit-learn has the function for that. train test split, you can ask, I think there's a parameter in a train test split, and the scikit-learns, which, if you use stratification, let me just, from sklearn, model selection, import train test split. There are lots of variables. Stratify. If not none, using this as a class as the class labels. So you basically if you pass here your array of labels, then it will split correctly. So we can actually test it. So we'll do train test split x train x. Sorry, it's not x train. It's data iris data iris target, and then stratify equals iris target x train x test y train y test. Let's see, y train y test. Now that's actually hard to say what's going on because shuffling would have done the same thing. So what we can do is we can do counts. We can say unique np unique, and it says return counts. So y test return counts true. 13, 12, 13. Well, it's because I asked for kind of a rounding number, so let me ask for some nicer number. Actually, I didn't ask for anything. So this would be test size 0.2. Yeah. So now you can see it precisely gives me 10, 10, 10 in the test, and it'd be 19, 19 or 80, 80 or whatever number, 40, 40, 40 in the train set. So it now completely separated classes. So this is the best way to do if you have classification. So just do stratified sampling always. You're going to be safe. If somehow it's very hard to do, then the second best bet would be shuffling if your classes are even. Okay, so that was an important remark because without this shuffling or stratification, we're going to get a really strange results. Now I've done this here by hand, stratified sampling. So now I'm going to build a tree, but first of all, let's take a 5-minute break. It's about time. See you guys in 5 minutes. But actually, if you remember from the graph that we saw a few minutes ago, you might not need to go any further. So in the regression tree, you always go all the way to the bottom till you get a single sample, right? Because that always improves your mean squared error. But here, once you end up with the pure set, you're done. And if you happen to end up with the pure set at one of the higher nodes, there is no reason to split it. Your gene is already 0. You're not going to make it any better. So in other words, if you end up with the nodes that are pure before you reach the bottom of the tree, that's okay. Just keep an eye on that. I put the entire 2 full levels, but you might end up with a fewer nodes. So this is fine. Don't feel obligated to fill every single node. It has to be a valid tree. All right, so also there is a find, again, I simplify, as you remember, right, how we implemented it. And if you're not, please look at my implementation. Programmatically, algorithmically, when we need to build a tree, we gotta iterate over every single column, right? We don't know which column, which feature would give us the best split. So we have to try every single one of them. So try the first one, try every single value, see if we found the best possible split, and iterate. We're not gonna do it with Excel because it would be very, very tedious. So we know by looking, or I know by looking at the tree previously built, that the first 2 splits will be on the petal width. So I put it here, so there is no mystery around it. Petal width in both cases. So the top level splits on petal width, and the 2 levels below may split on petal width, right? But so you can ignore other columns, basically, right? We're going to work with one feature. But in the implementation, you can't ignore other columns. You have to try them all. So what's the first step? Well, the first step, we need to sort by the column. Well, we don't have to sort, but it will be very inefficient scanning, right? So if we sort by petal width, we now have all our things, all other values in order. So our criteria would be less or equal, right? Remember, so petal width less or equal to some value. Which value should I try? What do you think would be the best bet here? Should I do it one by one, or you have an idea where I should split? Well, this here, right? Why is that? Well, you know the answer, right? So unlike a regression, that's why I said classification would be easier to do with the Excel, because humans are actually really good at classifying things. So it's really kind of obvious here, right? So we're not going to find a good split, because then other nodes will be mixed. So the best would be to separate all zeros into one side and everything else to the right side. So that's what will make this tree kind of much easier to build. But let's support this idea, right? So let's see. So Gini, let's say I'll do here. First, I'll just a little bit off. We know what we expect, but let's confirm that actually our formula works, right? So what's the Gini for the left side? 0. We don't even need to calculate it, right? Well, for the right one, it's going to be more complex now, right? So it will be 1 minus ratios of others, right? So what's the total number we have here? So we have 15, right? The total is 15. How many zeros do we have? 1. How many ones do we have? Well, 1, 2, 3, 4, 5, 6, 7. 7, and I guess we have 8 twos. 1, 2, 3, 4, 5, 6, 7, 7. I guess 7. I guess they're all even, right? So I haven't counted before. So 177. Okay, total. So what are the ratios? So these are the absolute numbers, but remember we need ratios. What are those? Just one by the other, right? Okay. Okay, we're almost there. So now I actually want to square this. That's a bit excessive. And finally, I do 1 minus all of this, right? This, well, minus this, minus this. 0.56. So that's my Gini for the second node. Now, a very subtle thing, which actually throw a few folks on the regression tree as well. So left node is 0, 0, right node is 0, 5, 6. But we can't actually sum them up or kind of average them, because what's important part is how many samples we have. So we need a weighted sum. Because imagine you have a giant node that has a very low impurity, like a very, very pure, like almost pure, like giant node. And then you have a tiny node that's very impure. If you naively look at just the impurity numbers, you'll get like 0 and 1 and maybe 0.5 in the other, and you'll say, well, that's a bad split, because the other split gives me 0.2, 0.2, which is 0.4 or less. But because you have a giant node, your actual misclassification error would be very, very low, because most of the samples would go to the big node, and it's going to be very, very accurate, right? So these are just ratios. What we need to do is we need to actually do the weighted. And weighted means you take the value, multiply by the ratio of samples in the left node versus the ratio of samples in the right node. So in this case, it would be 0 multiplied by, so how many do we have here? No. So 6, and the total number would be 21, right? 6 over 21, and this would be 15 over 21. So these are our weights. So now we need to multiply these two numbers and sum them up. and the sum would be obviously first to 0. So 0.4. 0.4 is actually the right answer here. So don't forget to weight your genies across the values, across the nodes. Okay, so our first split gives us 0.4. I'm gonna save it here. Okay. Now let's shift by 1, and we expect what? Better or worse? Higher or lower? What is better? Higher or lower? Lower. So we hope we'll get the lower one. Okay. Again, so what's the gene in the left node? 0. And the right node, well, we got to calculate, right? So now we don't have the first class, it's gone. The second one would be what? 7? Is it 7 of 14 now? And also 7 of 14. Okay, so now we need to square them. Sum them up will be 0.5. 1 minus 0.5 would be 0.5. Right? 1 minus 0.5 and 0.5. Okay, now we need to do the weighting. So the left one gives us 0, so we can simply ignore it. Whatever multiplied will give us 0. What's the weight for the second node for this 0.5? 14 over 21. .33. So our genie here is 0.33, which is better. Okay, makes sense. So now let's see, let's make one more step, see if we overshoot a bit. What do we expect then? They get better or worse? And higher. Okay, well, let's see if that actually happens. Now in theory we can, I mean in practice when we build the algorithm we cannot stop here because, well, we don't really see what's going on further. The computer doesn't see it. It needs to try everything to make sure genie doesn't get suddenly better. Okay, so what's the genie in the left node or the top node? Well, it's not 0 anymore, right? Well, the very first thing, because now we have two classes mixed up. So now I have to do a bit of work here. Huh? You already know what it is? How is it 50-50? Okay, let's think about it. Is it 50-50? 50-50 would be if my probability of predicting ones and zeros are basically random. But zeros are much more reliable here, right? So I'm going to come up much more accurate predicting zeros. So this is definitely not going to be 50-50. The simplest thing, let's just calculate, right? So the ratio of zeros is 6 out of 7, right? The ratio of ones is 1 out of 7. Sorry, it's 8, yeah. We keep shifting samples, it gets confusing a bit, right? So 1 out of 8, okay. So I'll just square them right here. And now 1 minus, oops, 1 minus, minus 0.88. That sounds a lot. Yeah, hold on. So this is 7. Oh yeah, right. Yeah, I see what's going on. Okay. 7 over 8 squared. Yeah. 1 over 8 squared. Okay, it's much better. 0.22. So 0.22 is in the left node for now. We also need to weigh it now, right? We can do it right away. So the weight on the left node would be what? 8 over 21. When I have 8 samples on the left node, right? And so our total left part of the Gini calculation would be 008. Okay. On the right one, we're going to have what? We're going to have, how many ones do we have? 6 out of 13, right? Because 8 and 21, 13. And here we have 7 out of 13. Okay. Yep. Come on. It's just gonna punish you for any mistake. Okay, so we squared and now 1 minus each of them. 0.5, and now we need to do weighting, which would be 13 of 21, right? So 0.31. So 0.31 plus 0.8, our finals would be 0.39. 0.39. Which is higher. So we would pick, based on these three calculations, we would pick this split, obviously, right? Makes sense. But you need to, obviously there's not much left here to finish, so if you continue, you'll probably just need to do a few calculations to split it correctly, which is fine. But when you implement it, you'll have to try every column and every combination, every split point, and find which column and which split point on that column gives you the lowest total Gini, which is weighted. That would be your ultimate split that would go into the tree node, and that's how you implement your actual tree. So you need to try every single one of them. So if I were to continue, I'll get 21 Ginis for just petal width, then I'll get 21 more for this one, 21 more for this one, and 21 more for, so I get 84 total? 84 total calculations. And it'll be the lowest of them all that will tell me which column and which value I get a split on. So we already know the right answer is. But if you really want to prove that that works, and you have a couple hours, you can do it. So now definitely your tree algorithm should do it, because that's the only way it will work. Now once you split, same thing as split at this level. So actually this is the wrong split now. Let me reset that. So this would be the best split so far. It will be a little bit more confusing over here, because you see that's why there's this 2 in the middle. So if I didn't have the 2, that would be way too easy. It would be you just split across the thing. So here I need to figure out where actually it should be, because now you're going to be mixing up values. So once I split here, now all the left nodes go to the left node. Sorry, the top rows go to the left node, and then bottom rows to the right node. So what we're going to do next with the left node? Nothing, right? So we already get the best possible purity. Every single one class will stop right here. That's it. The left node no longer grows anywhere. We're done. So when you implement your tree, don't forget to check that the Gini already reached 0, because you'll be trying to split to make it better. It'll spin, but it's not going to make it better, because it cannot be better than 0. Now the right one, we now pretend that this is our entire data set, right? And we simply repeat our process recursively. So same thing, you create the same class that you have your root class, subclass, pass a subset of indices. Again, if the indexing caused some issues, to figure out how to do it, you have my implementation now online. Please take a look, see how the indexing is done. You'll pass the subset of these rows, and the algorithm is the same. It now only sees this data and says, okay, where should I split my data here to achieve the lowest weighted Gini in my subnodes. Again, in your algorithm, you'll try every single column. By hand, you don't need to. This column would give you the best splits. So just try only one column here. Once you do that, you'll build a tree. Let's do the root node right away. So 21, what's the value in the root node? Who said that? Can you speak it? I speak up. 777. Does everyone agree that it's 777? I see the question is, what is 777? Okay? Is it 777? So remember, in the classification, the value is basically the counts of our samples that happen to be in this node. And in the root node, we have kind of everything that came to us. And what came to us is 7 zeros, 7 ones, and 7 twos, unless I made a mistake in filling these rows, right? So we got 21 samples. Our value is not particularly amazing, but makes perfect sense. It's just the root node, so it has everything. So Gini. Now, when you calculate Gini for the root node, you don't do the split, remember. The split doesn't exist yet, so we should have calculated Gini before. So let's actually do it. So it's a root node, has everything in it. So we have 3 classes. What do we have? 7 over 21, 3 times, right? And then I'm going to square these. Again, I'm going to be punished, man. All right, it did something for me. No, I did the wrong thing. And I guess it would be 11, 11. And now 1 minus 3.11. 0.67. 0.67. Yeah, that could be that. Okay, does everyone agree it's 0.67? We just followed the formula, but we actually had this recently. It was somewhere here. It was last time. There you go. Because this is your tree, right? Yep, 0.6665. So that's our formula is right. We got Gini, and now we have a split, and the split would be what?
Do we take the 0.2 or do you do the average of that and the next one? Like
what is the right answer?
In the previous case, we did the average of this one and the next one, n plus 1.
So what should be the split? What's your best guess? What should we do? 0.2? Average it. So there are 2 choices, 0.2 or average what? 0.2 in 1? And it would be what, 0.6? Let's see what the right answer is. It's actually 0.8. Oh no, never mind. So ignore this. This is actually just a coincidence. My data set is different. So actually Gini is right, almost, because our samples are mixed equally. The counts don't really matter. But this is a different data set, so obviously the split point is different. But the short answer is yes, we need the average. Because when we train, we try to prepare for the future. And here there is really no reason for us to prefer one or the other. I mean, you could argue it should be less or equals 0.2, but somebody else could argue less or equals 0.9999999. And it would still achieve the same result exactly, right? Based on this training set. So if our split point is 0.99999, right? Well, since we have equal, we have to be careful about this. And I need a lot more zeros. There you go. Rounding rules. This will still split in the same way. It will still be split over here. Both values are right, but we have to have one. So which one is the best one? So we don't know anything else. We should pick the middle and say, okay, we'll pick the middle. It's the most conservative bet here, right? So that's why we're going to pick the average of one average of these 2 values, 0.6. So that's our split. So in the future, we might see values we have not seen that might have 0.5 or 0.9, and now we'll split them best on our best approximation. That's it. So the root is actually filled out, and we can now actually fill out the left one. So what's the left one? How many samples do we have? 7. All right. What's our value? So the counts of classes, right? How many zeros do we have? 0 class we have 7. How many classes 1 we will have? Nothing, right? Gini. Should we run a formula, or are you guys ready to guess it's 0? 0. All right. What do you think our split will be here? No split, right? Because we're done. It's a Gini 0, it's pure node, there is no reason to do anything else. How do I cross it out?
Can you go over what the value is 700? I thought it was like more like 007, no?
So this is in the order of your indexing of your classes, right? Usually the way classification works, your class names could be anything. So in this case, actually the class names are names of the colors, like Virginica, Versicolor, or something else. But they're usually pointless from the algorithm perspective. What you do, create indexing from 0, 1, 2, 3. In this case, our classes are 0, 1, and 2. So this array is ordered in the same order. So we have 7 elements of class 0, We have 0 elements of class 1, we have 0 elements of class 2. We're done, right? All right, what about the right one? Since we split, we can do that. Samples. 14, value. 077, right? It would be complementary to what happened to the in the left. And Gini, we actually didn't do that, right? Or did we?
I think we did compute for the whole right, for the right side.
Is it 0.39? No, I forgot what it
No,
was.
that's if we did the split.
Oh, let's do it quickly. All right, so it would be 7 over 14, right? Twice. Now 0.5, right? So we're going to square it, become 0.25. 0.25. 1 minus 0.25 minus 0.25 would be 0.5. So Gini would be actually 0.15 here. And the split, we don't really know. So actually your job is pretty much just fill in here. Or here and these two nodes. Right? So which in classification should be pretty straightforward. Did everyone get this? Where these 7s and 0s and other numbers come from? Classification tree, that's what we just saw. I'm not going to post my Excel as modified, but you can look at the video and just fill it up. So if you don't remember what just happened, you can look at the video. I also like you to implement, and then a couple of programming assignments. So the classification tree in Excel to get a sense how the tree works and how you calculate Gini. It's a pretty simple formula. You just need to fully internalize it because it will be coming up a lot in the future, and you will also use it. We also encounter it as a test. So make sure you are remember the formula. Accuracy score is really a simple function, but we need it now in our library. So please add it. If you miss some functions from your library, just copy them from my implementation. So after today, you should have a full set of functions. And a decision tree classifier. So if you ignore this one, I can probably just remove. It's posted, but don't worry about the score. So just make sure init, fit, and predict are implemented. You can take your tree if it worked well, based on the grader, if you're happy with it. If not, you can take my tree. You just need to modify a couple of things. What you calculate as an error, which should be Gini instead of the mean squared error, and they change the value from the number to an array of numbers, right? And also change how the predict function works, because it's now returning the probability. So predict will return the probability of this class. So instead of giving me a number 1, should be class 1, you return, actually it would be confusing, it should return 2 numbers. It should return actually a full distribution. So I'll correct my notes. So the predict function should return, let's simplify it. So just return a class. So I'm going to run on my test examples. I'll know what has to happen, so return a class. So in other words, predict should return 0, 1, or 2, whatever class it should be in there. Because if you want to return probabilities, you have to return the entire array for each input. For example, if I pass a single sample, you can tell me 10% probability of class 0, 80% probability of class 2, and 10% probability of class 1. So it's going to make our API a bit more complicated. It's the right API, but you'll get the idea. So we're not going to do it in this.
So we'll return just 0, 1, or
Just return the class that is the most likeliest class for your prediction. Don't return probabilities yet. That's okay. But you get the idea, right? That the actual probability is what you want to get. But you need to have the all probabilities of all classes. So
quick question about confusion matrix. The one that you had like in the case of...
Don't forget that. And make predictions for the grayed out areas here. This will be a test set. So now you have your inputs. You pass them through your tree. And you make predictions. And prediction would be what?
That's the training part.
No, but what kind of prediction? What do you expect? A class, right? So it's not going to be an actual real number. It will be with 0, 1, or 2. Right? Hopefully they match, but if they're not, they're not. That's perfectly fine, right? Is your prediction. Once you have your class, and the class is the actual, so we know what we actually should have gotten. Once you have your predictions for all 9 test examples, you can calculate the accuracy, which is one number, how many correctly you got, how many correct ones you got. And then you can calculate your confusion matrix. So the confusion matrix is the measure of accuracy or predictive accuracy. It has nothing to do with the values that are written in the nodes.
The prediction part, you are saying how many zeros were there, how many ones were there, and how many twos were
There are no how many's are here. Here you return the actual prediction. What do you think this row, the first 4 values, if you pass into your model, will be the predicted label, predicted class? It will be the 0 or 1 or 2. There is no uncertainty here. I mean, there is uncertainty, but we're ignoring that. We're just picking the likeliest class, no matter how confident or unconfident your model is, and says that's what I predict to be, and you put it here. And it becomes a prediction. Now, you calculate the prediction by looking at your tree and calculating those probabilities, right? So, for example, if I'm here, my prediction would be 0, always. If I'm here, you can pick either. You can predict 1 or 2. Both are equally bad predictions or equally good predictions. So 1 would probably be natural because you just go in the order, but both are correct. Correctly wrong, or basically both are equivalent, right? So, but that's one prediction. When it goes out, it's being matched with the rest of the test set, and we'll see how you did. And then the confusion matrix is basically on the left one, you know what you expect, right? Here you expect 7 zeros. And the way you write them down, let's do it real quick. Let's say my prediction 0, 0, 0, 0, 1, 2. Let's do 1, 1. Okay, I have 5 zeros and 2 1s. So what's my confusion matrix is?
0, 2, 0.
What should I put here? 5. Okay? So now think about this. My row should sum up to 7 total zeros. But this gives me distribution of my predictions. Columns shows how actually I predicted them. Of this 7, I said 5 were zeros, and then what? 2 were 1s, and 0 were 2s. This is it. Same thing for 1. It should sum up to 7, should sum up to 7. But your actual predictions would be whatever they will be. So in an ideal world, all your things should be in diagonals, right? So only 7, 0, and nothing else. But in reality, they're going to start mixing or being confused. That's where the word confusion matrix comes from. It shows you how your model confuses classes. What class with what the problem happens. Because it's not always uniformly wrong. Usually, unlike regressions, which are kind of a uniform continuous prediction variables, in classes, you will often see that some of your classes are doing great, but some are doing really poorly, because for those classes, maybe the predictive variable is very weak, or the model is not the best fit, or things like that. So that's where confusion matrix